All right, this video is going to talk a little bit about graphs and some of the characteristics of graphs. One thing that we talk a lot about in pre-calculus is the symmetry of a graph. There are three major symmetries or three simple symmetries that we talk about a lot. There's x-axis symmetry, saying we're reflecting something over the x-axis. And very simply, if you take your points, well, if you're on that top graph, you'll notice that x, y, right, any coordinate on our graph could be sort of flipped over that x-axis, reflected past that x-axis, which basically we're traveling vertically, then we're changing the y-coordinate to be a negative y-coordinate. And vice versa, negative y would become positive y. If you end up still right on top of your function, there's really no change to the function, right? Those points end up right on top of each other, then we say that it has x-axis symmetry. Function related, that means that f of x, all the y coordinates, would be equal to negative f of x, all the negative y coordinates. No matter what you plug in for x, you should get a point on one of those two lines, and all those points are equal. Which means if we want to check things out and we want to algebraically verify, what we'll want to do is replace the y with negative y and see if our function looks exactly the same, see if there's absolutely no difference. The same thing goes for an even function. An even function is y-axis symmetry. If I reflect it over the y-axis, it only makes sense. The positive x's relate to the negative x's. So again, to check algebraically, if I take x out and plug in negative x, right, and my function looks exactly the same, there's really no change, then we have y-axis symmetry, or we have what we call an even function. An odd function is one where the negative f of x will equal f of negative x. It's going to look a lot like a rotation around the origin. Not only are we reflecting the x's, but we're reflecting the y's. We're kind of going both left and down, or basically to the right and up, basically sort of pinwheeling around that origin. Negative f of x, so similar to what we did for the x-axis, right, reflecting over the x-axis, and negative x inside, so reflecting over the y-axis. If we reflect over both x and y, we end up with an odd function. So a great way to check that, again, is plug in a negative x on the right and a negative y, replace x and y with negative x and negative y, and again, nothing changes. So in that case, again, on a graph, we can look at it and kind of guess that maybe these symmetries happen, but we don't want to guess. We want to be very precise, because what if they're just not quite perfectly that pinwheel, or not quite perfectly symmetrical and that simple reflexive symmetrical? What if we want to test them algebraically, and let's make sure they really are? So taking a look at that function at the left, if we want to test and see if it's an even function, remember our test for an even function was replace x with negative x and see if we get back the original function. So what we can do is write this down and say y equals, I'm going to take out all the x's and I'm going to replace them with negative x. So negative x to the sixth plus negative x squared. Oops, and I did that in the wrong order there. Careful, we're just taking out x, which would have been inside the square. So I need to square the whole thing. And plus 8. Well, any number to the sixth power, right, is an even exponent, which means any negative number is just going to disappear. That negative to the sixth, or if I took negative 1 to the sixth, remember that's going to be positive 1. So negative x to the sixth is really just x to the sixth. Same thing goes with squaring it. So again, negative x squared is really just x squared. And 8 didn't even have an x, so that's really just 8. And notice that looks exactly like the original. So what we can say is that equaled y, right? And oftentimes we'll call this f of x at the start, and then this was sort of a f of negative x, and therefore we're saying that f of x, right, equals f of negative x. And so if, or I could say since, probably be a better word, f of x equaled f of negative x, therefore These are an even function. And we've proven that, again, plugging in a negative with that x changed nothing. We'd want to do the same thing over here at the right. Again, if we want to prove that it's an odd function, again, our test for that was plug in negative with the x and with the y. Right? We want to reflect both over the x-axis and the y-axis. So this time I'm going to say 13 over negative x to the 7th minus negative x times negative y is equal to 4. Well, negative number to the 7th power is going to stay negative, so this became a negative 13 over x to the 7th. Negative x, negative y, those are going to cancel, so this is still minus xy and equal to 4. And it'd be pretty easy argument to make, taking a good look at that. Again, we still have a minus xy, we still have a 4, but there's that new negative on the outside, right? That new negative outside the fraction. And I don't think there's anything we can do algebraically that's going to turn that statement back to the original. So I would say, therefore, since, again, f of negative x didn't equal negative f of x, therefore not odd. It didn't satisfy the statement. I hope that helps you with symmetry of functions. Again, a couple good practices. If you have any questions, make sure you talk to your teacher, and have a great day.